Let's talk about the simple concept that is complex numbers. So we've seen this before back when we studied polynomials. We're going to elaborate and go deeper than you may have ever thought possible. We're going to uncover some truly remarkable things as we explore complex numbers in a little bit different light than we're used to. So just to review, if we have a complex number z, a plus bi, the real part of z is a, the imaginary part of z is b, the magnitude of z, also called the modulus of z, would be the square root of a squared plus b squared. And the argument of z, I'm going to hold off on that for a second, but that is the angle that z makes when measured from what traditionally would be considered the x-axis. But we're talking real and imaginary axes now. This is what we would call an Argand diagram. So z1 could be plotted 3 in the real direction, 2 in the y direction. There's our z1. We can think of it as being a vector. The argument would be that angle. That side is 3, that side is 2. Well, how do we find that angle? It's the inverse tangent of opposite over adjacent. So b, the imaginary part, over a, the real part. And we're going to use this as we go into it, and we're going to look at this no longer in a rectangular sense, but we're going to introduce the idea of a polar coordinate system. So now instead of having an xy axis, what we have are a bunch of concentric circles with a radius of 1, 2, 3, 4, so on, and we're measuring angles going around. So when we plot points in the polar system, we're using r comma theta, not x comma y. Let's plot z1 so that the magnitude of z1 is 2. So that means that z1 will be on the second ring here. And the argument is 60. In other words, pi over 3. So it's that angle. So we're turning up that far. And we are out 2 rings from the center. So there is our z1. What are its rectangular form? Well, here we have 60 degrees. We have a modulus of 2. If we want the rectangular form, we're looking for the y-coordinate and the x-coordinate, and that's just right triangle trig. So the x-coordinate is going to be the modulus 2 times the cosine of 60 degrees. The cosine of 60 degrees is 1/2. So 1 is our x-coordinate. Our y-coordinate would be 2 times the sine of 60 degrees. The sine of 60 degrees is square root of 3 over 2. So the y-coordinate is square root of 3. So its rectangular form is 1 comma square root 3. Let's go ahead and plot another complex number, another point on this complex plane, and I want you to pause the video and try and plot this point right now. So we're on the second ring. The modulus is 2, and we're an angle of 7 pi over 3. Well, where's 7 pi over 3? Well, we're going around 1 full time. That would be 6 pi over 3. 7 pi over 3 would take me up to right there. So there is my point. And if you compare it to where we were before, that's the same complex number. So z2 is equal to the z1 that we saw in the previous point. And how much do these 2 points differ by in terms of their argument? Well, they differ by 2 pi. And we can summarize that and say that if z1 and z2 are indeed equal complex numbers, then the modulus of each of them has to be equal. And the argument of the first one will differ from the argument of the second one by some multiple of 2 pi. In the previous example, the argument of z1 and z2 differed by exactly 2 pi, or 360 degrees. So here's a problem to solve. We want to find all r and theta such that z1 equals z2. If we know the modulus of z1 and z2 are these expressions, and the argument of the two complex numbers are expressions involving theta, we know r is going to be greater than 0. Okay, so how do we do this? Well, if we know that the two complex numbers are equal to each other, that means the two moduluses have to be equal also. So r squared equals 5r minus 6. Well, this is just a quadratic. We can solve this for r. R could be 2, or r could be 3. Cool. What about the angle? Well, we know that the argument of one complex number has to be equal to the argument of another complex number plus a multiple of 2 pi k, or a multiple of 2 pi. So we could rearrange that statement and say that the difference between the two arguments has to be some multiple of 2 pi. So 3 theta minus theta plus pi, that's the difference of the two arguments, that has to equal some multiple of 2 pi, where k is an integer. So what we have is 2 theta minus pi equals 2 pi k. So 2 theta equals pi plus 2 pi k. And theta would be pi over 2 plus pi k. Now, what angles can be true? Well, any multiple of pi added on to pi over 2. So we actually have a long list. Pi over 2 works. That's when k equals 0. If k equals 1, we have 3 pi over 2. If k equals 2, we have 5 pi over 2, and so on. And also going the other way, if k is negative 1, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on and so on and so on. And this list is infinite. A lot of times you'd be given a domain for what theta could be.